Okay, so today we're going to continue with our phase diagrams. And yesterday we ended our lecture with the phase diagram with an intermediate compound. So this was an example between copper and zinc. And we talked about a couple of different phrases. So eutectic, anyone remember what eutectic transformation means? But eutectic is in one concentration. So at some constant concentration. So the points we're going to talk about here are along some constant concentration on the phase diagram, so a vertical line on the phase diagram. And as we lower the temperature at the eutectic point, you go from a liquid to two different solids. It doesn't have to be alpha and beta. It could be any two solids. But it doesn't go through a liquid plus solid transition stage. Okay? So I don't see a eutectic point on that phase diagram. If you do see one, let me know. Yeah, so you have the eutectoid, right? So eutectic, I don't see one. Do you see one? Liquid goes to two solid. No, I don't see one, but if you do, let me know. And you're right, there is a eutectoid. And in this particular case, delta goes to gamma plus epsilon. So it's one solid phase at some constant concentration. As you cool it down, it goes to two solid phases that are different than the parent phase. So most of the time you go from one solid phase to two solid phases, but the parent phase is one of the two solid phases, right? So you might go, let's see. If you were to go from here, this point down to here, you go from beta to alpha plus beta. So beta is is a parent phase, is the phase that you started with, but it's also one of the two solid phases that you end up with. So that's usually what happens. But at a eutectoid, you end up with two phases, neither one is a parent phase. And then you have something called the peritectic, where you get a solid phase plus a liquid phase that goes to a different single solid phase. In this case, it would be here. You have this, the phase in here would be delta in liquid, and as you cool it down, it goes into just one solid phase, epsilon. And the reason why material scientists have bothered to give these specific names, these point specific names, is because when you have phase transformation that happens along these points, you get something different in terms of microstructure. And we'll talk about that in more detail. But remember, if you have a binary phase diagram, something like this, liquid alpha, alpha plus beta, beta, liquid plus alpha, liquid plus beta. Okay, so it's for a simple binary diagram with a eutectic point here, is if you cool something down, you'll get a microstructure that has alpha with beta particles, because alpha forms first. And if you cool something down here, you get beta with alpha particles, because beta forms first. If you cool something down along the eutectic temperature, you get layers, something like that. Layers of alpha and beta, because they form at the same time. Okay, so they're called invariant points because it happens only along a specific concentration. These points give you different microstructures, and that's why we give them specific names. Any ideas why? This is not obvious, but any ideas why when we get two phases that form at the same time, we tend to get layers as opposed to just particles of alpha and particles of beta? So how come when we go down the eutectic temperature, alpha, beta forms at the same time, How come we get layers of alpha and beta and not something like, maybe like this, where we have beta particles and alpha particles? So it has to do with how these phases are formed. So if you have a liquid, this is my element A here and my element B here. And if you see here, the eutectic point is closer to the A side, so it's A-rich, if you want to call it that. It has more A than B, right? Okay, so you have particles of A and B in this liquid. So that's, say, here. When we go through the eutectic point, you're going to get alpha and beta. So let's say we end up here. Okay. My alpha is going to have a concentration here, and my beta is going to have a concentration or a composition here. Right? That's how we find out the composition of each phase. So now you have two phases, alpha, which is very A-rich, and beta, which is very B-rich. Two different phases with two very different compositions. So basically, in order to form that, all the B's have to get together to form the beta phase, and all the A's have to get together to form the alpha phase, right? To get together, they need to diffuse. They need to migrate through this material. So it's diffusion, and we know diffusion doesn't happen quickly necessarily. And so the shortest path for all the B's to get together and for all the A's to get together is in the layered form. So if we have something like this, let's say the B is all the yellow. All right, so this is my alpha, and this is my beta. And then if I have a different microstructure, so maybe it's like this, and this is my B, something like that. Okay? I have these two options to form alpha and beta simultaneously. And let's say I have a B element here, somewhere in the alpha. And it needs to migrate to a beta phase because it needs to go to the B-rich phase. I only have to migrate a short distance in order to get to the beta phase, right? But if I had a B element here, I would have to migrate for a long distance. I have to diffuse a much longer distance in order to get to the beta phase. Okay, so it has to do with which kind of microstructure is easiest for the material to form. This involves the least amount of diffusion, therefore it is easier to form than something like that. Doesn't mean that this cannot form. Let's say you give it lots of time and temperature for diffusion to happen, and you let it sit at that elevated temperature for a long time, you could eventually get to something like this. Why would there be a driving force to get here if I leave it for a long time? So why would anything change? Why would any system change? Because it wants to go to a lower energy state. If it's already at the lowest energy state, there's no driving force for anything to change. It'll just sit there forever, as long as you don't change the environment, right? So in order for there to be a change in the system, that must mean that it's going towards a lower energy state. So the question is, why would this material be a lower energy state than this material? So I'm telling you that if you leave something like this for a long time, you give it enough energy for the diffusion to happen, it will eventually end up here, looking more like that. So why would that be? What is the driving force here? So this has fewer grain boundaries than this. And grain boundaries is where the crystal structure is disrupted. Any place where the crystal structure is disrupted, so like a dislocation, grain boundary, surfaces, pores, so holes in the system. Any place where the crystal structure is disrupted is at a higher energy than the rest of the system. So this material has lots of grain boundaries, right? And this material has fewer grain boundaries. So you can imagine the fewest grain boundaries might be like that, just 2 grains. One is alpha, one is beta. Very unlikely to happen, but that would be the lowest energy that something here can have. One of you had a really good question yesterday, and that has to do with the tie line. If I have a material that's here, that exists here, I draw a tie line across, and this material is made out of liquid plus beta. The question was, why is the beta in here with the composition, or has the composition of where this tie line meets the liquidus line, right? So we did a couple of practice problems. We saw that the beta within this phase, you could find out how much A and B is in there by looking at where that tie line crosses the liquidus. But why is that? It's because in this phase, at this temperature, there is no beta phase that is thermodynamically stable with a composition with less B than here. Do you see that? If I have a beta, let's say that's here, so that has a composition with less B, a lower percentage of B than this one. This phase is not thermodynamically stable at that temperature. If I go up, it becomes a liquid. And so I can't get a solid to come out of the liquid with any composition less than this line. So that's the minimum amount of B I would have in my beta phase in order to have a solid phase at that temperature. Same thing here. I don't have a liquid phase that is stable with more B than that, or less A, at that temperature. So if I have more B, at this temperature, the liquid would be a solid. And so that's my minimum A for the liquid phase. So let's go back to the intermediate compound. So this is one example. Here's another example. Okay, so this is magnesium and lead, and at roughly 81 or 80 point something weight percent lead, you have an intermediate compound that's Mg2Pb. So that intermediate compound exists only at one specific concentration. Instead of a region, right? Usually we have a single phase that occupies a region. This one is just a line, but that's still okay. So everything here is alpha. Everything within here is alpha and Mg2Pb. And here is beta, and everything in here is beta and Mg2Pb, magnesium lead. So does this one have a eutectic point, this phase diagram? A eutectic. Do you see a eutectic point on that phase diagram? It's right here. Go from liquid to 2 solid phases. How about a eutectoid? Is there any place where you get one solid goes to 2 different solids along a single concentration? So I don't see one, because this goes to one solid to 2 different solids, but it's not along a single concentration, right? You could change a concentration and that still occurs. All right, I also don't see a paratectic. So a paratectic would be a solid plus a liquid going to a different solid, single solid phase. I don't see that. And let me ask you, what is the melting temperature of pure magnesium? Estimate is fine, roughly 630, 640, something like that, right? Degrees Celsius. Okay, what is the melting point of pure lead? 325 degrees Celsius. As you add, so let's start with pure magnesium. As you add a little bit of lead into the system, do you expect your melting temperature to change? You start to add a little bit of lead into your magnesium. Would you expect your melting temperature to change? Or would it stay the same? Okay, it'll change. Will it go up or down? Down. Very good. What is the lowest melting temperature of a magnesium-lead compound? Any concentration. So if you could find any concentration, what do you think is the lowest melting temperature? 250 degrees Celsius, something like that, right? So here. And in fact, I missed this one. This is another eutectic point, right? So we have two eutectic points on this phase diagram. So the lowest melting point for any compound within the system is about 250 degrees Celsius. If you were to draw a microstructure for a material that's at 300 degrees Celsius and 50% lead, so right here, go ahead and draw it yourself on in your notes. What do you think that might look like? You probably get grains of which phase? Alpha, because it forms first from the liquid. And then you might get pieces, magnesium, lead, embedded within the alpha. And I would expect that there to be quite a lot of, at 50 weight percent, I would expect there to be quite a lot of magnesium to lead, right, in my system. More magnesium to lead than I would have alpha. So I would draw more of these. What would you draw as your microstructure if you were at 300 degrees Celsius, but at 90 weight percent lead? What would that look like? So still at 300 degrees Celsius, but this time we have 90 weight percent lead. Go ahead and draw the microstructure in your notes. Something like this. Because I have a liquid and a solid. The solid is a magnesium to lead compound. Okay, one more question. Let's say I have a material that is 50 weight percent lead and 50 weight percent magnesium. When will that material start to melt? If I have something that's 50 weight percent magnesium, 50 weight percent lead, when will that material start to melt? 460, 470 degrees Celsius, something like that. When will that material finish melting? Completely liquid. 555, 560, something like that, right? So now let's look at an iron carbide phase diagram. So when we were looking at the video about the Wootz steel, this is the phase diagram that the professor and the farrier were looking at. And this is probably one of the most commonly used phase diagrams. And as you can see here, the phase diagram only lists weight percent of carbon up to 6.67 weight percent, because anything past that, it's not something we would use as a steel. I won't ask you where the eutectic and eutectoid points are because it's labeled on the phase diagram, but you can see them here. It has one eutectic point and one eutectoid point. And 100% iron is alpha. And then at carbon, 6.67 weight percent, that's called a carbide, an iron carbide, Fe3C. Okay, so those are two endpoints. And because this is so commonly used, there are actually names given to the different phases. So instead of just calling alpha, beta, gamma, etc., they're actually names. So alpha is called ferrite, and it has a BCC crystal structure. Gamma here is called austenite. It's FCC. And Fe3C is called cementite. And it's orthorhombic, the crystal structure. I think that's all the phases that's on here. Let's see. If I have 2 weight % carbon, when would I expect that material to start to melt? 2 weight % carbon. So I have a steel containing 2 weight % carbon. When might that material start to melt? 1,130 degrees Celsius up here, right? It's not here, but what happens at 720 degrees Celsius? Something happens, right? There's a line there. Alpha or ferrite turns into gamma or austenite. So there is a phase change at 723 degrees Celsius, but it's not melting. The ferrites turn into austenite. You continue to raise the temperature at 1130 degrees Celsius, you start to melt. You continue to raise the temperature and roughly 2,100, something like that. 2,100 or 2,300 degrees Fahrenheit, you would expect the entire material to be liquid. So now we look at the same diagram. This is the same as what we looked at before, but now it shows you the microstructure. So here are, because again, steel is such an important material that people have given it lots of names. These are the phase names. These are the phases. The microstructure is something called perlite. And that's alternating layers of ferrite and cementite. So that's called perlite. So here, this area where you have a grain, but you have alternating layers of ferrite and cementite. The way that looks in a micrograph, if you look at it under the microscope, the lines would look wavy, kind of looks like pearls. So that's why people called it perlite. So let's say you have something that happens along here, this green line right here. So you start at 912 degrees Celsius, you look under the microscope, you would expect to see 100% austenite because that's the phase that is present here. So you look under the microscope, you see grains, and they're all austenite grains. You lower the temperature to this point here, and you start to see alpha phase or the ferrite phase start to form out of the austenite. So you get austenite, and then these little particles are the ferrite. They start to come out because you're in the region where you have both ferrite and austenite. You continue to lower the temperature, you get more ferrite, more of the austenite is converted into ferrite, and you lower the temperature some more. The ferrite stays, the ferrite that was formed before stays, but the austenite that was there before splits into ferrite and cementite. Because you're getting ferrite in here, and these ferrite, there's not a lot of driving force, so they're already ferrite. It doesn't need to change into ferrite and something else, because ferrite is stable at this lower temperature. But the austenite, this austenite, it is not stable at the lower temperature. So it needs to change into ferrite and cementite. And so because both phases are forming at the same time, they tend to form layers. So you get this perlite structured embedded between ferrite. Okay, now let's look at something else. Let's look at this green line. So same thing, you're starting at 100% austenite. So you look under the microscope, you get grains of austenite. You lower the temperature here, and now instead of ferrite particles growing out of the austenite, you get cementite particles growing out of the austenite. Because in this region, you have austenite and cementite as the stable compounds. You lower it some more, the cementite is going to stay the same, but the austenite will convert into alpha and cementite, again, forming layers because it's going into two different solids at the same time. So now you see that picture up there, you get cementite between the perlite phases, or the perlite microstructure. So by looking just at the microstructure, you can tell if you have a hypoeutectoid steel or a hypereutectoid steel. So if you get cementite pieces between the perlite, then you know your carbon concentration is greater than 0.76. If you get ferrite in between the perlite, then you know your carbon concentration is below 0.76 weight percent. And then if you go from here along the eutectoid, then you get just perlite. You get austenite that splits into ferrite and cementite at the same time, so the entire structure is perlite with no ferrite or cementite in between the grains. So this is the end of the portion where I wanted to talk about phase diagrams. But I want to give you a little bit of time to talk to each other, make sure that you understand, and then I'll give you a little bit of time to ask me any questions if you have any about phase diagrams. And I'll think of some questions to ask you too. Let's test your knowledge a little bit, okay? So let's say I have 3 weight percent carbon at 1500. So go ahead on your own, in your notes, draw the different microstructure as you lower the temperature to 600. So the first one should be 100% liquid, right? We start at a place where it's 100% liquid. You lower the temperature. What phase will form first out of the liquid? Gamma or austenite. So you get little pieces of gamma or austenite solid within the liquid. You continue to lower the temperature, and right as you cross the 1147 degrees Celsius temperature, when you get below it, your gamma will stay the same. That's not going to change much. But your liquid is going to become what? Your liquid will transform into gamma and cementite. And as you lower the temperature, let's say layers of gamma and cementite. As you continue to lower the temperature, let's say just before here, just before this, the eutectoid temperature, 727 degrees Celsius. So you go from 1147 or 1146 to 728. Would you expect your gamma phase or the austenite phase to become more or less or the same? Would you have more austenite phase at the higher temperature, at the lower temperature, or would you have the same amount of austenite phase? It'll become less. Okay, as you lower the temperature, you'll actually have fewer or smaller austenite phase, and you could tell because of this line. At higher temperature, you have the tie line, and you can see calculate the percentage of austenite. At lower temperature, you have this tie line, and you could calculate the percentage of austenite. And so as you lower the temperature, if you did that calculation, you'll see that austenite becomes less. The percentage of austenite in the structure becomes less. Okay, so then you drop the temperature some more. Now to 600, what will happen then? The cementite probably doesn't change. The cementite that's already in your structure, but all of the austenite will change into ferrite and cementite. And so you can see by adjusting the carbon percentage, you can change the microstructure quite a bit. And there are important regions of carbon. So if you have carbon that's less than 0.76 weight percent carbon, you tend to get one kind of microstructure. If you have something between here, 0.76 to 2.14 weight percent carbon, you get another kind of microstructure. And then between 2.14 to higher weight percent carbon, well, to 4.3, you get another type. And then between 4.3 to 6.7, you get another type of microstructure. So a lot of times when you look at steel, they'll actually tell you the carbon percentage. And the reason is because it gives you some idea of the kind of microstructure you might have for that steel and gives you some idea of the properties of the materials. So again, phase diagrams tell us what is thermodynamically stable. So whatever is showing up on the phase diagram, that is existing at the lowest possible energy state. It doesn't tell us how fast it'll get there. So you lower the temperature, you would expect there to be, let's say you're at 600 degrees Celsius. You would expect there to be alpha and cementite. But it doesn't tell you how big the grains are or how fast that phase will form. Okay, so it doesn't tell you anything about the rate of the system. Okay, so in order to talk about the rate, because that does matter, right? When you were watching the Wootz steel being made, they would quench the metal sometimes, so cool it very quickly. So cooling it quickly and cooling it slowly gives you a different microstructure. And that does matter. So the next topic we will talk about is kinetics, which is talking about the rate of transformation. So we know now what kind of phases and microstructures are possible based on the phase diagrams. Now we will talk about how do we get there, how fast. Yes?
Can we ask what is the final graph at 600 Celsius?
Yes. So I have something like this, right? I have this is my austenite and my cementite. And let's say my cementite is pink. I won't draw all of them. So I have my cementite and my austenite. And my austenite will change into, so we lower the temperature, the austenite goes to and now this is alpha, and the pink is, so all of my austenite phases will become ferrite and cementite. But my cementite probably won't change because there's no driving force. It's already cementite. It's stable at that temperature. It's not going to, nothing much will happen. But the austenite is not stable at the lower temperature, right? And becomes ferrite and cementite. All right, so now let's talk about kinetics. So that's a rate of reaction or transformation. So in order to understand kinetics, we need to talk about how the different phases form. So we talk about things like this, right? That when you go from liquid, you cool it down, you get austenite particles within the liquid. Well, how does that happen? So how do phases form? How does a new phase? So let's say I have a liquid made out of iron and carbon. I'm going to have, if it's within my iron carbide phase diagram, I'm going to have a lot more iron than I have carbon, just a few. Definitely less than 6.7 weight percent carbon. Okay, so I have a liquid that is mostly iron with a little bit of carbon. I start to cool it down. And in my phase diagram is showing that as I cool this down, I should get austenite phase. So the gamma phase. So I cool this down, and I should get the austenite phase. Okay, that's what the phase diagram is telling me. But how does that phase actually form? So it forms a nucleus first. It's also called nucleation. And nucleation is any time you get a particle, a small particle about 100 to 1,000 atoms or molecules. So you get a small particle within this liquid, that's austenite. And there are two different ways nucleation can happen. One is called homogeneous and one's called heterogeneous. So we'll talk about the homogeneous first. Homogeneous nucleation. So this means without a catalyst. So this nucleation happens without anything additional that you're providing to the system. So why would new phases form? What's the driving force for a solid to form out of the liquid when you lower the temperature? Because at the lower temperature, the solid has a lower overall energy state than the liquid. So that's a driving force, to get to a lower energy state. So you have two competing energies here. You have the volume free energy, and you have the surface energy. Okay, for the new phase to form, this will be negative. New phase is more stable, so the overall free energy of the phase is negative. So new phase. So you had something that is 100% liquid. You lower the energy, you get little particles of, in this case, austenite to form, right? The austenite forms because it has a lower overall energy compared to the liquid. But now you're introducing surfaces. Before, there is no boundary between the liquid and another liquid. Now there is a boundary. Now you have a surface around the particles that wasn't there before. So you're creating surfaces. And surface, we know, is a place where energy is higher because the crystal structure is disrupted. Okay, so this will be positive because you're creating areas of higher energy. So that's what's happening. The competition of energies is happening when you form a new phase, the nucleation. So the volume contains areas where you have lower energy. The surface has high energy. So what kind of shape do you think the nucleus will take on? We know the overall system wants to have the lowest energy possible. We're forming a volume that has low energy compared to the system, and a surface that has higher energy. So what shape do you think my nucleus is going to take on? Spheres, because spheres have the lowest surface to volume ratio, right? We want to maximize our volume and minimize our surface because the volume is where the energy is low, surface is where our energy is high. So naturally, when you form these nucleus particles, they're going to be spherical. So now that we know we have spheres, we could calculate the change in energy of our system. So this is called change in free energy. It's also called Gibbs. So that's why we use G, named after somebody who came up with this idea. So the Gibbs free energy, the change in the overall free energy of the system will be a competition of the volume energy and the surface energy, right? So I have my volume energy, G sub V, times the volume, how big my spheres are, plus my surface energy, so 4 pi r squared. That's the surface area of my sphere times the surface energy. This term will be negative because my delta G sub V is negative. This term will be positive. And so my delta G can be negative or positive depending on how big my nucleus is or my nuclei are. So as my nuclei get bigger and bigger, my surface energy is going to get bigger and bigger as a function of r squared, right? So it looks something like this, a parabola. Okay, so this is my 4 pi r squared. The x-axis is this radius of my particles. So as my particles get bigger, the increase in energy due to the increase in surface area will also get bigger. As my particles get bigger, the decrease in energy due to the increase in particle size will also get bigger as a function of r cubed. So it looks something like this. So I'm going to get the combination of the two will look something like that. So initially, I have an increase in energy as my nuclei form. But as the nuclei get bigger and bigger and bigger, then the overall change in energy gets lower or more negative. So you have some energy barrier to overcome when the nucleation happens. So this tells us the kinetics. So this is delta G. So that's the activation energy needed. At this point, you have R star, how big the nuclei need to be for particles to grow. Right? So if you have nuclei that's smaller than R star, then the system will go to a lower energy state if the nuclei continue to shrink into nothing. If you have a system with a nuclei greater than R star, then it is thermodynamically beneficial, or the system goes to a lower energy state if the nuclei keep growing. So R star is where the nuclei needs to get to at least some size before it is favorable to continue to grow. So let me do a real quick calculation to show you what that R star and G star are. So if I look at this graph, which is this equation, right? The yellow curve describes this equation. At the maximum of that curve, with respect to R, the derivative of that equation should be 0, right? Because that's the maximum. So if I take that equation and take the derivative with respect to R and set it equal to 0, that's where my R would be R star. Right? So let's do that. Just taking the derivative of that equation and setting it to 0. So R star would equal negative, so I just combine everything, 2 gamma divided by delta GV. Okay, so the size of my critical nucleus depends on my surface energy and my volume free energy, which makes sense, right? The higher the reduction in free energy as I form my nucleus, the smaller the critical size needs to be, because there's a large driving force going there. The higher my surface energy, then the bigger my nuclei need to be in order for it to continue to grow. Okay, so it's a function of my surface energy and my free volume energy. So now if we plug this back into here, we can then find our delta G star. I'm just going to plug this back into that equation. If I solve that, I get 16 pi. So the activation energy can actually be quite large, depending on the particle, the amount of free energy. So we have something. Let's just look at the simplest phase diagram possible. So you get alpha plus liquid. So this part is where so let's say I'm at this concentration of A plus B. Okay, I go from here to just below the liquidus line. Okay, so I start to get some alpha. Or at least thermodynamically, I should expect it, right? But my system is telling me that there's some activation energy that's required because the surface area that needs to be formed and so on and so forth. okay? Do you think that the activation energy will be higher? So let's call this point A and point B. So will the activation energy be higher at A or B? We know our activation energy is dependent on two things: surface energy and the free volume energy, the change in free volume energy, right? Okay. Do you think the surface energy will be different between A and B? Probably not much, because the surface is the surface. I mean, that the discontinuity in the crystal structure is not going to be that different between the slightly higher temperature and the lower temperature. So the surface energy will stay about the same. So the only other thing that can change is a change in free volume energy. So which one do you think will have a higher reduction in energy when it forms a solid? Point A or B? How many think it's A? Raise your hand. How many think it's B? How many are not sure? So no one raised their hand for A. For those that raised your hand for B, why do you think that B might have a higher reduction in free volumetric energy? So let's talk about water. Okay, so water at 0 degrees Celsius, water can be water or ice. It's about the energy, the inherent free energy at 0, it's about the same. That's why water is both, can be ice or water at 0 degrees. That's a transition. You lower the temperature, which one now? So now let's say you are at -2 degrees Celsius. Which phase will be more stable? Ice or water? Ice, right? And what about if you continue to lower the temperature at -20 degrees Celsius? Which one will be more stable, ice or water? Ice. And in fact, it is much more stable, because as you lower the temperature, the driving force for water to go into ice becomes higher and higher. So the lower the temperature, the more reduction in the free volume energy for water to turn into ice. Okay? Because at close to the transition point, they're about the same. The free energy, volume free energy for the two phases are about the same. But if you continue to lower the temperature, then the new phase, the reason why it will form is because it starts to have a much higher reduction in the free volume energy. Okay? And so point B, you're right. Point B have a higher change in free energy, and therefore the activation energy will be, if everything else is the same and this increases, then activation energy decreases, right? So the activation energy will be higher at A and lower at B. So in fact, in homogeneous nucleation, sometimes you have to go quite a bit under the phase transition temperature in order to overcome this activation energy. And that's something called supercooling. So the ice may not form at 0 degrees Celsius. You might have to go to -5 degrees Celsius for your ice to form. And that has to do with the activation energy to form ice out of water. And this phase transition goes the other way as well. There's something called superheating. And that's actually a little bit dangerous. So if you take water and you heat it to 100 degrees Celsius, you expect it to evaporate, right? Water goes to vapor. But there's an activation energy for that phase transformation as well. So sometimes you have to take it above. This happens very rarely, and I'll explain a little bit why it happens rarely. But sometimes you could get water to be superheated. So maybe it's at 103 degrees Celsius, but it's still liquid. But you give it that extra little bit of energy for it to overcome the activation energy, then all of a sudden, all of the water will evaporate. And so it's like a small explosion. There's, all the water evaporating at the same time, as opposed to just slowly evaporating like when water is boiling normally. Okay, so that could happen sometimes if you're heating up water in the microwave and it looks like it's hot, you take it out, and then you like hit it against something, and all of a sudden a lot of the water become vapor at the same time, and it could splash out and burn you. So that has happened to people before, and that's because of superheating. So why does it not happen more often? Is because most phase transformation happen heterogeneously. So this is with the presence of a catalyst. So when you have a catalyst, it can help you overcome the activation energy. And what are some catalysts? It can be impurities, surfaces, any kind of defects. And the reason why this helps is because it decreases the surface energy. So instead of forming a perfect nucleus within a vessel, so let's say you have water and you're trying to form ice, instead of having to form small, perfectly spherical ice particles, now you're forming along the surface an ice particle. So one, it reduces the amount of surface you have. And two, it actually is the surface between your vessel and the water. There's some surface energy there as well. So if you're creating an ice particle there, you're also reducing the amount of that interface that was already there, right? So you're actually having surfaces and defects can help you overcome the nucleation energy. So that's a catalyst. So if you're watching a pot of water boil, you'll see that most of the time your water vapor, the bubbles, form along the edges and the bottom of your pot, right? If you're watching it boil, you'll see the bubbles start to kind of grow on the edges and the sides and the bottom of your pot, and then it leaves that and comes to the surface. Okay, so what you're seeing is heterogeneous nucleation. So homogeneous nucleation is very, very rare. You have to have a very pure material, no defects, very perfect material, and also very little difference in surface energy between your container and your material. So most of the time, what we observe in nucleation is heterogeneous nucleation. But even with all of this, we still haven't talked about kinetics yet, because nowhere in here is it time dependent, right? So if we want to talk about rate, we need to have time. So number of nuclei that has R greater or equal to R star, the critical nucleus size. And N star is equal to K1, which is some material constant. And so this is where our rate comes in. I don't know if you remember this equation. We've seen it a couple times before. Where else have you seen this kind of equation? When we talked about our diffusion coefficient and our diffusion energy, the rate of diffusion. So this is where our rate comes in. The number of nuclei that has the required size to grow is a function of this. And time is embedded in this area. So this is a Arrhenius equation. This is so this is just a graphical representation of what we just talked about. By having a catalyst, you could lower your overall activation energy for the particles to form, but your R star is not going to change. So the critical size required for your nuclei to form is still the same. It's just the activation energy has been lowered by the presence of other surfaces or impurities or defects. So let's look at rate. How fast do these things form? Temperature, and this is our rate. This is nucleation. Okay, so at temperatures below the melting point, you will start to have nuclei form. It will start slow, And as you get lower and lower and lower in temperature, the rate will get higher and higher. And the growth will be something like this. So why does it grow faster at higher temperatures? Because there's more energy for diffusion, right? So anytime we have a nuclei that needs to grow, atoms need to diffuse to that nuclei. And if you have very low temperatures, then you have very low rate of growth. And if you have high temperature, you have a high rate of growth. And so if you look at both of them combined together, you're going to get something like this. And so this is sort of the region for, so you're going to have a region for optimal phase transformation. It's not going to be right at the melting temperature. It'll be slightly below to accommodate for the activation energy that's required. And it's not going to be too low in terms of the energy because it is going to require some temperature for diffusion to occur. Sorry, this is a combination of, the red line is a combination of the two white lines. So if you add the nucleation rate and the growth rate together, you get the red. Because you need, in order for phase transformation to happen, you need both, right? You need to have a nucleus, and that nucleus needs to grow. So I think I will stop here, but the rate will depend a lot on the temperature, as shown here. So the rate, how fast transformation happens, is temperature dependent. So we'll continue this next week.